parameter epsilon lambda. It's given by that. I panicked for a second, but if I had a k there, I'd have a k there, and this has a Poisson distribution as well. And because we're looking at 0, there's no term here, and it all falls apart. Unfortunately, God, I can't erase that. I guess I can erase that. Let's just do this first. So let's collect terms. So we've got for the zeros or the ones. You see, with the ones, I always have a width epsilon. I'm always looking at an interval of width epsilon and saying there's a 1. So I get this common term that appears n times. Cool. And the other thing is ugly. It looks horrible. I have a product of these guys. All right, so that looks pretty horrible. But do you see something happening here that's nice? Yeah, so is there a mistake somewhere? I'm sorry?
Don't the one conditions imply the zero conditions since the interval is disjoint?
I'm not sure what you mean.
It can't happen one without it not happening.
Well, look, I'm only looking at differences. That's the trouble. So like I have to exclude that there aren't a million jumps in this period. So if I was only looking at jumps there and there, I'd get into trouble there.
Not the possibility of another jump.
Well, there could be 100 jumps in this interval.
Okay.
Yeah. So I got to be careful. Yeah. I don't think there's any more compact way of going from this to this. Yeah. Yeah. I don't see it anyway. But yeah. So somebody pointed out this telescopes. So everything cancels out here, except those damned epsilons. So you get and that, one second, is there a, so what is this horrible thing in the end? Anybody work it out? So here I've got that thing there. And when I go through and I take the exponential of the sum, it's a telescoping series, and I get a minus lambda times minus epsilon n times, so I get n lambda epsilon. And then the only thing that's left is the Tn. And that's all in parentheses and up top at the top of the exponential. So we can write it down. The whole thing boils down to lambda epsilon to the nth power times e to the minus lambda Tn That's pretty wild. So what's really important is that the Tn's important, but the rest of the Ti's are irrelevant. All right, it's completely uniform, which is sort of what we're going for. Now, guess what we're going to do now? So the statement is not about the TIs, it's about the delta I's. And I really hate to do this, but let's go and do it. It's good practice. How would I say something about the delta I's? So we didn't want the density for the taus, we want the densities for the deltas. So let's just go through and do some calculus, right? We know that the taus are the sum of the delta I's. All right, we have a random walk for these taus. And so we can come up with a matrix here relating the deltas to the taus, namely tau 1 is just delta 1, and tau 2 is the sum of delta 1 and delta 2. You get a wonderful matrix here, which anybody can invert and play around with. All right. So you could say this is, T equals m times delta, if you like. And so then we know how to do the calculus, right? We have the density, the density for one is related to the density for the other. Oh, excuse me, I skipped a step. Remember, I erased my goal. Our goal was to find this p epsilon to find the density. Everybody, what's the density? I've got an epsilon at the end just sitting there. So I was basically supposed to take this, divide by epsilon to the n, and let epsilon go to 0. Well, there's no limit to take. So it's just lambda to the n which is pretty amazing. All right, and so then to come up with, and that's f of t if you like. So if I want to go to the taus, the deltas, now I don't know what symbol to put in here. We don't have a symbol for deltas. So deltas are the random variable. I'm looking at the density as a function of some variables, some demi-variables. What do? I take the density for this, and I plug in T equals m times delta. And then I have to divide by the inverse. How do you do calculus again? The determinant of m inverse, is it? Yeah. Yeah. I always have to completely rederive this whenever I write it down. So thank you. So there it is. All right. And the determinant of this monster, because of its structure, is just 1. And then here, the beautiful fact is you get a lambda to the n, and then you get an exponential of minus lambda. This function only depends on the last guy. And Tn is just the sum of the, UNs. So I can erase that one, yeah. Isn't that pretty? I mean, it's, it's a little pretty. So that's the joint distribution of ID random vector. All right, so that's it. So it took us some time, but we can prove A equals B by using our basic calculus stuff. So this is really stuff reviewing noise 1. How on earth do you go from B to C? This was the hard work, okay? There's nothing, it's not so bad after that. You tell me. So basically, we want to say that if these guys if the inter-event times are ID exponential lambda, then we get this density, this conditional density, and it's basically reversing what we've already done. Okay, but again, it's worth doing. But stop. At this point, your eyes are glazing over. Questions? Anything? Crystal clear. All right.
So this may be a stupid question.
Yeah.
But did we get back to that n factorial over tau n?
No, we haven't done C yet. So we proved that A equals B. But here, I'm going to prove this is constant, right? On this domain. This is the domain because we know that these random variables, the tau 1 through tau n are ordered by definition. So we know that they live on this region. I leave it to you to prove that the constant has to be this.
Okay,
Yeah, it's just a normalizing constant. So next we prove B equals C. But we don't have to go through all this work again because really everything else is repetition of these ideas, so I won't really do them. So what do you do for B equals C? And B implies C. So we're given that the delta i's are exponential with parameter lambda, IID. And then you can reverse the steps. I've erased it now, but I did that transformation between the deltas and the taus. I could just do that again, and I get this formula once more. I get that if I look at the density of tau 1, tau 2, and I'm going to go to tau n plus 1 just for the fun of it. I need that. That's just going to be equal to what we saw before. Okay, so we've proved that. Just look at your notes. We said that there was a one-to-one correspondence. There was a mapping between the taus and the deltas, and so we could map densities one to the other. So this was done already. It's in your notes. We proved this, and then we basically proved that's equivalent to the IID exponential distribution for the deltas. Cool. Now, here's what we're going to do. So I want to condition on n tau equals n, and I'm going to choose my tau in between the last time points here. So I'm giving values like this. It's a natural thing to do, right? Because I'm interested in conditioning on being exactly n events at time tau, all right? So tau, so it means that, so saying that n of tau equals, saying n tau equals n is exactly the same as saying that tau is greater or equal to tau n and less than tau n plus 1. So that's the event I'm interested in. And so now I can look at a conditional expectation, conditional probability. So I hate to write this down again, but it's okay. So I'm going to the same sort of event that I had before. So what am I doing here? So this is what somebody else tell me what this is. This is a conditional density of these time points. Condition on n tau equals n. So it's hard to write this down. So it's like I've still got my epsilon to the n in here. So it's like a conditional density of all these time points and one beyond given n. And you notice something special here. Conditional probabilities are defined as the probability of an event and the event you're conditioning on divided by the probability of that event that you're conditioning on, right? But you notice this and here is redundant. That's what I said before. All right. So, and so, because this is redundant, what we actually get is that this density is just equal to this guy here divided by this probability we don't know. Okay, so going through all this work just to sort of burn this into our brains. Because I don't know how to think about conditional densities. I have to first look at conditional probabilities, and look at a cube like I did before, and let the volume of that cube go to 0. It's the only way I know how to think about this. And so I did all this just to impress upon you this extra thing that you have in the numerator is redundant. You get rid of it, and you're left with something you understand. This is exactly, the numerator is just this times epsilon to the n plus 1. I added 1 to n, that's why it's n plus 1. Okay, so that was the only reason for rewriting this crap. Okay, cool. So what's special about this? I'm trying to get that this is constant, and I've got an n plus 1. I only tagged in that n plus 1 so I could say this was redundant. What am I going to do now to get what I want? I'm with you. Somebody give it to me. So I've got when I have a density on n plus 1 dimensional random vector, but I don't care about that whole thing. I only care about the first n guys. So what do? Not condition, but get rid of it. How do you get rid of it? Integrate it out.
Integrate over that region.
Yeah, over the region. So it's basically, I'll put a ditto here. So I'm integrating this density over all Tn plus 1 in the range that we've considered, but that range is over Tn plus 1, tau n plus 1 is greater than tau. And if you work that out, you integrate, take one of these lambdas outside. I've got lambda times e to the minus lambda blah, and you integrate that, you're just left with the exponential. Phew. Okay, so we did it. That's a constant, right? I didn't say it didn't depend on anything. It depends on n, right? And it depends on tau, and it depends on the parameter lambda, and it depends on this unknown thing that we don't know anything about. But there you have it. This is constant. And it's just like exhausting to try to present this because it's so simple but so diabolical. So we proved it, and we get one more thing, right? I haven't told you what the probability that n tau equals n is. It doesn't matter, right? Because all I said was that this was constant. I claimed that this long discussion here of throwing down random points is the same as saying this joint density is constant. You just believe me on that one. But does anybody know what the probability that n tau equals n is based on this formula? How would you find it? You can integrate the left-hand side over its domain, and so if you do that, you're going to get 1 on the left-hand side, and the right-hand side you're also going to wait a second. So what is it? Somebody else tell me. So if I integrate the left-hand side of the region, I get 1. If I integrate the right-hand side of the region, I get the reciprocal of the constant. Now, that's a constant. I don't know why I kept it inside the integral. Okay, so it's basically what I have here in brackets times the volume, and you just have to believe me, it's tau n over n factorial. And then you go through and you take the probability that n tau equals n to the left-hand side. And you will get lambda to the n e to the minus lambda tau, tau to the n over n factorial. And that should look familiar. Yeah, the lambda and the tau go together. And yes, it's a Poisson random variable. Right. That's it. So from here, you just integrate. And so now you can see it's not that hard. I mean, basically, given the fact that this implies that n tau is a Poisson random variable with the right parameters. So that's the definition of a Poisson random variable of the form we want. To go from here to here, you have to basically extend this a little bit and say the increments are independent and that they all have a Poisson distribution, and it's the same set of stuff. So there's no new concepts there. All right. Okay, cool. You guys are awfully brave. I mean, I don't think anyone fell asleep. Maybe you did. I don't know. All right. Yeah.
Can you remind us again why that n tau equals n was redundant?
Oh yeah. Because I said. Yeah, because this is exactly how I defined. Oh yeah, this in a way this was a review. Remember, this was a way of saying that the jump times of n were in those intervals near t1, t2, t3, and so forth. And
Okay.
yeah, and actually, and really I cheated a bit because I have to make sure that my I think I have to put a minus epsilon there. I might have slipped that out. You forced me to write it out again.
I think I see it.
Now, I've got to be a little bit careful because I've got to make sure that, yeah, I definitely need this. I missed that, everybody. There was a mistake right there. So the event I was looking at is that there was the first jump was over here, maybe an epsilon window. The second was there. The third was there. The fourth was there. The nth was there, right? And the nth plus 1 was there, right? So at this point, there's been exactly n events, as long as the epsilon is ahead of tau. So we need that as well. Yeah.
So those tau are t.
Now, these are taus. These are the random variables. And oh, I see what you mean. You're right. Damn. Those should have been t's. I'm looking at probabilities of events. That's a mistake. Yeah. So my the event I'm looking at is probably tau 1 is in here, tau 2 is in here, tau 3 is in here. So I'm looking at the probability that they're close, but these are deterministic times, and all right, cool. Anything else? So no more about Poisson processes. So I mean, again, this was a bit of a detour, but it's I don't regret it. I hate to launch into a whole big topic, but we have to in a way. We have to start talking a little bit about what's next. And what is next? I haven't gotten any feedback about what you all want, except for the Markov chains. All right, feedback. That's cool. Reinforcement learning. No, that's another course. Yeah. I mean, I can't force you guys to learn about dynamic programming. I mean, that's too much. But let's talk about this. So what's next? So look at the syllabus. If you look closely at the syllabus, you'll see that there's a midterm in the middle of the spring break. And so you can ignore that in the syllabus. And you can probably ignore some other things as well. But what's next? And it used to be I couldn't say statistics. People they scream and run away. But now people associate statistics, as they should, with learning and inference and all those good things. I mean, statistics has always been a beautiful topic. It just sucks when you take it in like a first-year graduate course. It's awful, undergraduate. So I used to blow off the linear theory and say you can read this on Wikipedia. I mean, it's a huge field. I mean, if the theory of common filtering, you can take multiple courses on it. There are issues of observability, but that's more. You need to take a control course in a way for that. So I will sort of blow that off. But there's a lot of representation theory that's really cool. So in the linear theory, that includes things like innovations in common filter, which leads to the common filter. And this is something I've never blown off. It's fundamental, but the notion of innovations, basically what's new in my data. And this is a way of building numerical algorithms, recursive algorithms, all that. Once you get this, then deriving the common filter is some tedious algebra, and then there's a lot of theory there too that's quite elegant, but it's beyond this course. So I think I will sort of blow this off. I'll explain to you why once you understand what innovations is, this pops right out, but not much more. But besides that also is all the pretty approximation theory. It's like generalizations of principal component analysis. And if that isn't machine learning, what is? I mean, it's like the most basic tool in machine learning. So this Karhunen-Loew expansion that you saw is one example of that. I mean, really, that's what I mean in a way. What do we do, you know? And so there's that, and so I guess we get to work. So I think it'll be a similar style to the last lectures. I mean, not this lecture, but like the Brownian motion and SDE stuff, where I gave you the main conceptual picture and said, you know, go to a book if you want the details. This stuff is incredibly difficult if you go into the details, but the main ideas are beautiful and easy to understand without getting into the beautiful technical details. They're just hard. Anyway, but let's do the easy stuff, the really simple stuff first, and then move on to this. And I think, but that's when we get back from spring break, we'll get into the Markov chains. How's that? Is that a deal? But I think it's going to take us, I will see. Maybe even on Friday. No, but Friday should be a holiday. Thursday should be a holiday next week. I don't know. Some of you might want to get away early for spring break. I don't. You all tell me. All right, sounds like a plan. So, okay, in my world, I've got some observations Y that I'm taking a look at. I've got a state that I'm not observing directly, and I'd